Here's a quick thermodynamics question which looks at what happens to an ideal gas, which in this case is hydrogen, as it's cooled under constant volume conditions. So we're dealing with, as the question says, gaseous hydrogen, which has this volume and it's being cooled by an amount delta T, which is 55 degrees Kelvin or Celsius, because it's a change in temperature, so it could be either, but obviously we're going to use Kelvin as we should. And the question is, well, actually there are two questions. So the first one asks, find how much the internal energy of the gas will change, and then what amount of heat will be lost by the gas. Okay, now first of all, we have to look at the fact that the question is specifying standard conditions. So standard conditions usually means that you have a pressure which is 1 atmosphere or 10 to the power 5 pascals. That's the normal atmospheric condition, atmospheric pressure at sea level. And then we have the standard temperature at sea level, which is about 15 degrees Celsius, or you add 273 to get the Kelvin value, so that's 288 degrees Kelvin. Okay, so we're dealing with a container which has hydrogen in it, and the gas in here is being cooled down. Okay, so the gas is being cooled down and the temperature drops by 55 degrees Kelvin. So we have that the final temperature, let's call it T, is just T naught minus delta T, like this. I'll use numbers, I'll put in the numbers later. So let's try to find the answer to the first question, which is how much the internal energy changes. So we can say, using the first law of thermodynamics, we have Q is equal to W plus delta U. Now, this is a rigid container, right? Which means the gas doesn't do any work and there's no work done by the gas. So there's no work done by the gas and there's no work done on the gas either. So this is 0, which means that Q is equal to delta U, which in a way gives us a hint towards the second question, because if Q is equal to delta U, and if the question is asking for both, we just have to find one and automatically we'll find the other one, because they're equal. So the change in internal energy is going to be equal to the usual formula. So it's M times the specific heat capacity at constant volume times delta T, like this. And we don't actually know what the mass is. So let's see what we can do about that. We have delta U equals, and then we have um, M times CV. And actually this delta T, if you think about it, is going to be negative. So I'm going to write as minus delta T. Right. Now, we don't know anything about the mass, but we can find an expression for the mass using the ideal gas law. So in the first instance, or in the first state, we have that P naught times V is equal to M times R times T naught. So the zeros represent standard conditions, and then we have M equals P naught V over RT naught. So then we can rewrite this as follows. So delta U is going to be equal to M, but instead of M, we're going to write what M is. So it's P naught V over RT naught, and then times CV. Now CV is R over gamma minus 1. That's the definition of CV, and then it's multiplied by minus the change in temperature. So the R's cancel out, which is nice. And then we have delta U equals P naught V over T naught, 1 over gamma minus 1, and we can put a minus in front, times delta T. And at this point, we actually know everything. So we should be able to find out the value of the change in internal energy, and it's going to be negative, right? Because the temperature is decreasing. So the change in temperature is negative, therefore this is negative. We know P naught, we know T naught, we know V. So V is given to us as 5 liters, right? Which is, of course, 5 times 10 to the power minus 3 meters cubed, because we should use meters cubed for this formula. Delta T is going to be 55 Kelvin. We're not going to write minus because the minus is already taken care of here. And the only other thing left to do is to look at gamma, right? So gamma is the same as the gamma for um, diatomic gas, right? Because we're dealing with hydrogen. So hydrogen is H2. So you can use a table and you can find out what gamma is for hydrogen in this case, and just don't use the 1.4 value for air because it's a different kind of gas. But if you know gamma and if you put all the numbers into this equation, that should give you the formula that should give you the value for delta U. And we said previously that the heat is equal to delta U. So we'll also have that the heat is going to be equal to minus this whole thing. So we have P naught V over T naught, and then 1 over gamma minus 1 times delta T. And you can see that it's negative, which makes sense. And if it's negative, this tells us that the gas is rejecting heat to the outside. Okay? And if you put all the numbers in, well, technically you don't have to do this again because this and delta U are the same, they have the same value. So you just have to do it once. And that's the end of the question.